Welcome to the Depth Dive. Today, we're diving straight into something really fundamental in number theory, prime numbers.
Yes, absolutely central.
We've got some great sources here, foundational stuff, but also some articles looking at how primes, well, how they behave sometimes.
Indeed. For anyone starting out in number theory, primes are just, well, they're the building blocks, aren't they?
Completely indivisible, except by one and themselves.
And that leads to that unique prime factorization for every number greater than 1. It's, a cornerstone idea.
And helping us navigate all this today is the OEIS, the Online Encyclopedia of Integer Sequences.
Ah, the OEIS. An indispensable tool, truly.
Yeah, think of it as the ultimate pattern index for numbers. If you, the listener, come across a sequence, you check the OEIS.
It's often the first place to look.
So today our focus is very specific. Sequence A000230. It's titled Smallest Primes for Prime Gaps.
Right, and that title tells you a lot. It points us directly towards the spaces between consecutive primes.
Okay, so let's unpack that a bit. Prime gaps. What exactly are we talking about?
Well, it's pretty straightforward, actually. A prime gap is just the difference between one prime and the very next prime number.
Okay.
So think of the start of the primes, 2, 3, 5, 7, 11, 13.
Right.
The gap between 2 and 3, that's 1. Between 3 and 5, it's 2.
And between 5 and 7, also 2.
Exactly. But then between 7 and 11, the gap jumps to 4.
Ah, so they're definitely not all the same size. They vary.
They do. And that's where A000230 comes in. It gives us a very specific piece of information about these gaps.
Which is?
It lists the smallest prime number, let's call it fide, that comes immediately before a prime gap of a certain size.
Okay, let's use those examples again. A gap of 1.
The smallest prime before that gap is 2, because you have the pair 2, 3.
Makes sense. And a gap of 2, we saw that twice early on.
We did. Between 3, 5, and 5, 7, the OEIS sequence records the very first time it happens. So for a gap of 2, the sequence lists 3.
Got it. First occurrence and the gap of 4.
That first appeared between 7 and 11, so the sequence entry for a gap of 4 is 7.
So it's like the OEIS is flagging the starting point the first time each gap size appears on the number line. It helps organize how we look at these gaps.
Precisely. It's a way to systematically track the onset of different gap sizes. It's not just, a list. Understanding where these gaps start gives us hints about the overall distribution.
Right. And you notice just from those first few examples that the small gaps, like 1 and 2, they appear very early.
Gap size 2, that's related to twin primes, of course. They seem quite frequent, especially among smaller numbers.
But the sequence implies that for bigger gaps, we probably need to look further along the number line, at larger primes.
That's the intuition, yes. It feels right, doesn't it? As numbers get bigger, primes generally seem to spread out a bit more.
Which connects to something fundamental, the prime number theorem.
It does, absolutely. The prime number theorem gives us a handle on the average density of primes. Roughly, it says the density around a large number, $6, is about $1 log.
So, on average, the space between primes grows as the numbers get larger?
That's the idea. The average gap near $6 is roughly dunny.
Okay, but A000230 isn't about the average gap, is it?
No, that's a key distinction. It pinpoints the very first prime, where a gap of a specific size occurs. It's about the leading edge, if you will.
Now, we know primes go on forever. Euclid proved that, right? Infinitely many primes.
A beautiful, elegant proof, yes.
So how does that fit with the gaps between them? If there are infinite primes, do the gaps have a limit?
Ah, that's where it gets really interesting and maybe a bit counterintuitive. Just because there are infinitely many primes doesn't mean the gaps between them have to stay small.
Oh.
In fact, it's proven that the gaps can become arbitrarily large. You can find stretches of consecutive composite numbers that aren't prime as long as you want.
Wait, really? You can find 1 million consecutive numbers, none of which are prime?
Yes, or 1 billion, or any length you choose. Theoretically, you can construct such a sequence.
Wow, okay, that's quite something. Infinite primes, but also infinitely long potential deserts without primes.
It highlights the kind of irregular, almost paradoxical nature of their distribution.
So looking back at A00000630, if we were to compute more terms, we'd expect to find primes that initiate larger and larger gaps.
That's exactly what we expect. Finding the prime that starts, say, the first gap of size 100 or 1,000, that's going to correspond to a term further down in the sequence A000000.
And finding those primes, especially for really big gaps, that sounds computationally hard.
Oh, it is. It can require significant computing power. It underscores the effort involved in mapping out prime distribution, even just finding these first occurrences.
Which naturally leads to thinking about what we don't know. There are still open questions about these gaps.
Many big ones. For instance, while we know gaps can be arbitrarily large, how large can they be relative to the primes around them? Are there tighter bounds than we currently know? The prime number theorem gives an average, but the maximum possible gap near $6 is still debated.
And what about specific gap sizes? Does every even number eventually show up as a prime gap?
That's another great question. We see gaps of 2, 4, 6. Does every even number appear infinitely often? Or even just once? That's related to, but different from, the twin prime conjecture, which is specifically about the gap as 2.
So A000230, this sequence of smallest primes for each gap size, it's really a starting point. A way to frame observations before diving into these deeper mysteries.
I think that's a good way to put it. It's a concrete sequence, something you can compute and look at, and it reflects this mixture of structure and irregularity in the primes. Where does a gap of size 14 first appear? Where does 100 first appear? Asking these questions via A000230 gives us purchase on the bigger picture.
Okay, so let's quickly recap. OEIS A000230 catalogs the smallest prime number that kicks off a prime gap of a specific size. It shows small gaps appear early, larger gaps tend to appear later.
Right, aligning with the idea from the prime number theorem that primes thin out on average.
And it also highlights that gaps can be arbitrarily large, even though primes are infinite.
And it serves as a launch pad for thinking about those really deep, unsolved questions about prime distribution bounds on gaps. Which gaps occur, how often?
It really is amazing how simple definitions like what a prime number is can lead to such complex and ongoing mathematical quests.
That's the beauty of number theory.
So for you listening, here's something to maybe turn over in your mind. We've talked about the first time a gap appears, recorded by I00000230, but what about how often different gap sizes appear later on? Does a gap of 6 become more or less common than a gap of 4 as you look at larger primes? Thinking about frequency adds another whole dimension, something to ponder. Thanks for joining us on the Deep Dive.